And today I'm going to teach you about arc length. Yeah, so if you want to find the length of some arc that doesn't have like a straight line, which you know to solve using Pythagorean theorem, if you want to solve the curve of an arc, you could do this using integrals. So you could think of each little point on the arc as a tiny little slope. We'll call it dh. And if you have an infinite amount of those slopes and add them together in this way, you can find the arc length. So from A to B, you would have dh be the slope. And you can think of dh, since it's the slope, it changes in y and it changes in x in this way. So if you want to find the integral of dh in terms of dx and dy, you know that dx and dy make a right triangle with dh. So the integral of dh from A to B can equal this right here, square root of dx squared plus dy squared. Because by the Pythagorean theorem, dx squared plus dy squared equals dh squared. You take the square root of dh squared, and you'll get dh, which is this. And for Cartesian coordinates, you also want the integral to have dx in it, like factored out of it. So that way, when you take the integral, it goes away, and you don't have any messy stuff going on. So you take dx squared, square root of dx squared out of the radical, which ends up being dx, and this simplifies to 1, and this becomes dy over dx squared. Take the square root of that times dx from B to A, and that's arc length for Cartesian coordinates. Geometric coordinates, you want to have dx and dy, you don't want to have the integral be in terms of t, so you want the derivative instead of dx to be dt. So for a recap, parametric equations is when both the y-coordinates and the x-coordinates are affected independently by the value t. T isn't shown on the graph, but it's what changes x and it's what changes y. Yeah, so a little bit different from Cartesian coordinates. So what you would do is you would factor out dt out of both dx and dy, dt squared actually, because otherwise it wouldn't simplify to dt. You factor that out and you get dx over dt squared plus dy over dt squared. Take the square root of that times dt on an integral from A to B. Length coordinates is a bit more complicated. So you have the normal starter equation, integral b to a square root of dx squared plus dy squared. And you know that y is equal to f of theta sine of theta, where f of theta is equal to r. It's just kind of like how the radius is determined by theta. And x is f of theta cosine of theta. You solve for the derivatives, and they become pretty messy. You get derivative of f of theta times sine of theta plus f of theta cosine of theta for dy. Dx is f of theta cosine. Dx is the derivative of f of theta cosine of theta minus f of theta sine of theta. Dy squared ends up being this whole mess right here. F of theta squared times sine of theta squared plus 2 derivative of f of theta cosine sine of theta plus f of theta squared cosine squared of theta times d theta. Dx squared is also something similar to that. It's d theta squared cosine squared of theta minus 2 f of theta squared derivative of f of theta cosine of theta sine of theta plus f of theta squared sine squared of theta d theta. So when you add these together, this is equal to this, so they cancel out. So you end up getting this right here, which also simplifies to f of theta squared cosine squared plus sine of theta squared. So these two go to this, and you know that cosine squared plus sine squared is equal to 1, so you can just get rid of this. And right here, these two added up together becomes f of theta squared sine squared plus cosine squared of theta. Get rid of this, and all of this is times by d theta, by the way. And so you end up getting f of theta squared plus df of theta squared. You end up getting, and so that simplifies to this when you plug in into the dh formula. And you know that f of theta is equal to r. Three equations today. The first one for Cartesian coordinates is just 1 plus dy over dx squared, like this, dx. So that's for Cartesian coordinates. The next one, for parametric coordinates, from a to b, is the square root of dx over dt squared plus dy over dt squared dt. And the final one, for calculating polar coordinates from a to b, in terms of where f of theta equals r, is square root of f of theta squared plus the derivative of f of theta squared d theta. Right? And the way that you can conceptually think about how arc length works is if you have something like this, some equation, there's a bunch of little infinite points which have a little infinite slope like this, which is the change in dx over the change in dy. And you're calculating this. So using Pythagorean theorem and putting it in terms of t or in terms of x and y or whatever form of graphing you have, you could determine arc length. That's it.